in VLSI circuits. So this was ideal, right? This is an ideal. We went all the way to VDD, and we went all the way to ground when we were, depending on the P or the N was on. In real circuits, it's not so nice, okay? And this picture is trying to show you, for example, actually, before I talk about this picture, I'm going to draw another picture. Okay, I'm going to make an inverter. And this inverter has a capacitor on the output. So by the way, we're not going to have inductors and resistors typically. We're mostly interested in these transistors and the capacitors on them. But in this special case, we're going to look at a little different thing. So this is inside of our chip, okay? But somehow we got to get power to our chip. So here's the boundary of our chip. And this is one inverter, but there's literally billions of these things inside of our chip. But somehow we got to get a power. So outside of it, we have this power supply. Let's just say it's a battery in this case. Okay. And this is 1 volt battery. So this comes into our chip, and our chip has a package, and there's some pads, and there's a bond wire or a bump that has some inductance that goes in. And then it goes through this long wire in our chip to go into our inverter. And likewise, in the other, there's this bond pad and our package, and there's a wire that goes over, or a bump, and it goes over and it connects to the ground of our chip. Let's get rid of that. Okay, so this is what's happening in real life, okay? And I'm not going to draw it here, but let's say there's another inverter over here. And it's got a power supply connected over. Well, somebody said, I means higher current is the same volt, so doesn't higher current mean higher power? No, higher current doesn't mean higher power. It means, we're going to talk about this. What's the power consumption when you're charged? It's a good question. Let's back up here. So somebody, doesn't higher current mean higher power? So let's look at this scenario. This is a better one. What do I have here? Yeah, draw a new picture. Ooh. Let's do another scenario. Somebody asked me, doesn't higher current mean higher power? Okay. Good question. I always hate when people say, that's an excellent question, and they say it over and over again. I'm not going to say it. That's an okay question. So we said, let's say this is going from low to high and back to low again. And this is an inverter, so the output's going to go high to low and low to high. And this has a capacitor on it. So you see we're at 0. So we're at 0. So the NMOS is open, the PMOS is closed, and we're sitting at 1 volt. And these things can provide lots of current, but it's not dissipating any current, because in this situation we have the switch open. Sorry. We have this switch closed, and we have this switch open. And so we know there's no DC current, and this thing is charged up to 1 volt. So it can supply lots of current, but it's not wasting any current, because once we charge the capacitor up, the current stops, right? And then we go from 0 to 1. So then this switch opens, and then this switch closes. Now that takes some time, and when that's happening, and so what's going to happen is this is going to discharge. So all the charge that was on there is going to be dissipated through here. So initially, so what does that look like? It looks like, oh, all of a sudden we get this big current, and then it discharges down to 0. And when this current is flowing, it's wasting power. Now, the more current that has, the faster this happens, right? So we could have this, or we could have way up, way down like that fast. I don't know, I didn't draw that very good. Like that. But the amount of charge that we're dissipating is the same amount. So the total amount of current that we waste is the same. It's just how fast it happens. The more current I can supply through here, the faster I can discharge it. But the total amount of current, or the power, is going to be the same. I don't know. Does that explain it? Who was it? That was Max. You okay, Max? Oh, I don't know. The rest resistance there is get higher current. So we get higher current, but the power, because it's AC power, is going to be the same. I hope that explains that. Okay, let's, nasty. Let's go back to here. Oh, always does it. I have to learn how to turn that off. Okay, so this is the real life situation of this inverter inside of our chip. Now, it turns out these wires that connect to the power supply here into the ground are not perfect, okay? In fact, this wire here has some inductance, typically, and this wire that runs through here particularly has some inductance.
Recording in progress.
Oh, sorry, you can't. And some resistance. Sorry, can you? Somebody have a question? I can't. I didn't. You didn't come through. Somebody has a question. I don't know. Maybe that was just a random thing. So our wire that comes through here is, it's got some inductance. Let's just replace this whole thing. Got some inductance here, and some more inductance, and some resistance of the wire on the chip going into this. And likewise on the ground, we have the same thing. If I were to look at this, I have some inductance there, and I have some inductance of this wire and some resistance here. And so we can replace that. Now, what's happening is, let's say this was at 0 volts, and so this was, let's say it was at 0 volts, and this input went from 1 to 0. Okay, so what's happening here is this transistor was initially open, and then it's closed. So then it closes, and it tries to provide some current to charge this up to 1 volt. In our case, let's say it's a 1 volt supply. So that current has to come from this battery, right? This current comes right through here, all the way through there, goes down there, and it charges up that capacitor. But when that current goes through these inductance and resistor, well, first off, if I put current through the resistor, what happens to the resistor? I get a voltage drop. Now remember, this current is going to look like a peak, and then it's going to discharge. But when it's at its peak there, we are going to see a voltage drop. The current's going through here, so there's going to be a voltage drop across here, right? Call it VR. And what is that? And if I drop there, what's going to happen is, if I look at the voltage at this node that's charging up this capacitor, it was sitting at 1 volt all along because there was no current. And then it's going to temporarily dip down a little bit as we're sinking current through this resistance. And then eventually, once this is charged up to 1, it'll come back up. So this is, I don't know, we can call this VDD. The VDD at that node looks like, yeah, it's at 1 volt, it drops a bit, and then it comes back up. And it turns out the inductances do the same thing. What is it? I equals LD dV dt, and we'll get the same thing. We'll get a drop across this inductor. They both kind of work the same way, so it also causes this drop. And let's look at so then we charge it up to 1, and then we say, oh, and then we're going to go back up to 1 here, and now we're going to charge it back down to 0 volts. And so in this case, we're going to have current go through this way to discharge it, and that current is going to go through here. And if the current's going in this way, I'm going to get a voltage drop across here, plus minus. And I'm also going to get a voltage drop plus minus across these inductors. And what's going to happen is if we look at this VSS, it's going to be normally 0. But when the current goes through it, this node, you get a drop across there, this kind of jumps up temporarily. And it goes back down eventually once the current stops. So we're going to see these bumps on the power supplies here. And there's a term for that. We call it ground bounce. Or supply bounce, but the general term is ground bounce, we call it. And that's bad news because it means our supplies to our transistors aren't really ideal anymore because of all these parasitic capacitances or parasitic resistances and inductances. And what's even nastier is that, let's say we're sitting here, this inverter is not doing anything, but let's say this inverter over here is doing something. You know, it's transitioning. Well, if these are connected on the same wire, the current still has to come through there, but now it's going to discharge or charge this capacitor over here. I will see bounces on these nodes from other inverters. And realize we've got like billions of these inverters all over the chip, and they're all jumping up and down, so they're causing bounces on each other's lines all the time. What it means basically is that this power supply, yeah, it's 1 volt, but not really, because there's all kinds of bumps going on here at different times as others circuits switch and draw current through these parasitic paths. I shouldn't call it the parasitic resistances and inductances of these paths. So that's kind of a non-ideal. It's kind of like a noise. You can think about it as noise. I call it ground bounce, but it's a form of noise. Another issue that comes about is, let's say, let's do a little bit of erasing here. Let's just erase that. And let's say, you know, this inverter, its wire goes over top of this one and it comes out here. And, you know, we have some circuits over here. I'm not going to draw whatever, but they're driving these 2 inverters. And the wires that go to these 2 inverters are right beside each other. Like they're just nanometers apart or micrometers apart. They're right beside each other. And the wires have to come into the inverters from this place over on the left. Well, these wires that go by each other, it turns out they will parasitically couple to each other capacitively. If you take 2 wires that are very close, a small distance, there's a parasitic capacitance between them. And let's say this wire is going high and this wire is not doing anything. Well, because of this capacitance, we will see a small, you know, say we had this inverter was charging and discharging, we will see a small bump over here. It's not going to be as big as the, you know, this is going from 0 to 1 volt and back to 0. So this may not be that big, depending on how much the capacitance is and the impedance of the node, but we'll see coupling between it to cause some bump here. So we have noise on the power supplies, and we can also have noise on the gates or even on the outputs. If this wire goes through here, there'll be some parasitic capacitance will cause little bumps here. So because this whole circuit is compressed into this small area, we have these parasitic capacitances and resistances and inductances, we get all kinds of noise from the circuits coupling into each other. Does that make sense? So that's what this slide is talking about. We have these parasitic inductances that are given by this that cause voltages. We have parasitic coupling capacitances. We have supply bounce. We have current because of the charge and discharge of the capacitors that causes the current, that causes the voltage bounces. But basically, we have lots of noise in these digital circuits, okay?
So are those exact same problems that cause issues to deal with synchronous circuits?
We're going to see it's not so bad with synchronous circuits. And why is it not so bad with synchronous circuits is because I drew all these bumps. But if you have a synchronous circuit, they tend to happen at the same time if they're all being clocked at the same time. Not perfectly. They'll be spread out a little bit, but basically you have a clock change, you know, the clock is changing and a whole bunch of circuit change here and here, and you definitely get big bounces at that point. And then there's some propagation through the gates, so that may cause some later bounces, but a lot of the bounces happen at the same time, which tends to be, sometimes it can be good, sometimes it can be bad. But anyway, they tend to happen closer to each other in synchronous circuits. But in any case, there's noise. There's all kinds of switching going on inside your chip and coupling, so there's noise. That's the main point here. So we need to design our circuits so they can handle that noise. Ooh, excuse me. So